Okay, so welcome to the derivative of inverse trig functions. And our objective today is to take the derivative and to integrate inverse trig functions. Okay, what you have in your notes are all the inverse trig functions and their derivatives. However, the only two that we're going to cover in this video are arcsine and arctan. And as far as I know, those are the only two that are on the AP exam. Okay, so it's just memorizing these formulas. So to take the derivative of this, we're going to have to use chain rule. So we take the derivative of the inner function, which is 2. Then the integral of sine u is the square root of 1 minus u squared, where in this case u is 2x. So it would be 1 minus 2x squared. And so basically we would write that as 2 over the square root of 1 minus 4x squared, if I were to square those out. So that's how that would be written. I'm just making sure that I did that correctly. On an AP exam. Okay? The tan inverse of 3x. So u in this case is 3x. So it would be the derivative of 3x, which is 3. Let's go ahead and start with that. The derivative of 3x is 3 over 1 plus u squared. So that would be 3x squared. So we would write that as 3 plus 1 plus 9x squared. So it's pretty straightforward. It's just memorizing the derivative. So for this one, we have to use quotient rule. That's one of the reasons I love this unit, because we review everything. So quotient rule is low times the derivative of high. So u here is 3x. So that's going to the derivative of 3x is 3. And then 1, the square root of 1 minus u squared, 3x, quantity squared. So low times the derivative of high minus high times the derivative of the low, which is simply 1 all over low squared. So we could clean that up, not much. I'd probably just write as 3x over x minus 9x squared minus sine inverse of 3x. And then that quantity all over x squared. If you want to make that nicer than that, you go right ahead. Okay? So that's pretty much it for the derivatives, and you really need to only know arcsine and arctan. So then let's integrate that. So these are the forms for integration. In the past we've done arcsecant, but for this lesson we're only going to do arcsine and arctan, because I think those are the two that you see most about. Now these are a tad bit more difficult because you have to recognize the formula. So you have to recognize is the square root of a squared minus u squared, and it gives you u over a, and then a squared plus u squared gives you 1 over a arctan u of a. So you just kind of have to recognize the formula in this, and I might refer back to this. So we have to ask ourselves, does this look like arctan or does it look like arcsine? Or is it just a regular u substitution? Well, we can't use u substitution because if I let u equal to 9 plus 4x squared, then du is equal to 8x. And there's no x in this original problem. Okay, so we can't use u substitution. So let's see if it is an arctan. Well, if it's arctan, then a is equal to 3, and u would be 2x. So if u is 2x, we still have to figure out what is du. So du would be 2 dx. And we have 2 dx in our original problem. So I can replace 2 dx with du, and this becomes 3 squared, which is my a, plus u squared. And we know that from the formula that this is simply 1 over a times the arctan of u over A. And so, of course, I'm not going to leave that like that. That's 1/3 the tangent inverse of u, which is what, 2x over A plus C. Okay? Well, it's a matter of just recognizing what formula you can use. So this looks like arcsine, but this could also be a u substitution problem. So let's try u substitution. U is 1 minus 9x squared. I don't know where I got 19 from. So du is negative 18x dx. Now I have 3x dx in my problem, so I could make this negative 6 times 3x dx, and then divide by that negative 1/6. There's different ways of doing it. I just chose to do it that way. So now, so this is just a basic u substitution problem. So I have negative 1/6, the integral of du over u to the 1/2. And u to the 1/2 can be written as u to the negative 1/2. Doing antiderivatives on that, if I add 1, I get u to the 1/2. I need to divide by 1/2, which is the same as multiplying by 2. Let's see. So what is this? Negative 1/3 u, in this case u is 1 minus 9x squared, raised to the 1/2 power plus c. That's a secant problem, so I'm not going to worry with that one for now. Okay, now this one looks like sine inverse. Notice we can't do a u substitution. This du is negative 2x, and I don't have an x there, so this has to be sine inverse. So if this is sine inverse, then a is 2, and u is just x. So the sine inverse of that would be, let's see, I think it's, how do we handle a? I think a is on the inside. Yep, arcsine of u over a plus c. Went too far. So we get the arcsine of u over a. I'm sorry, and a is 2. And since I really didn't do a u substitution, I can use the limits that were given. So I have arcsine, I don't know why, I hope I'm not confusing you by writing this in 2 different ways, of 1/2 minus the arcsine of 0. And I'll leave you to figure out what that is. I know the arcsine of 0 is 0. Figure out what the arcsine of 1/2 is, and that's your answer. Okay, so once again, we're taking, this looks like tan. I can't do a u substitution because I get 2x. So I have to use tan inverse. So a is 3, and the u is x. So the 4 is going to be on the outside. So I get, it's 1 over a, so 1/3 times the tan inverse of x over 3, and I'm evaluating that from radical 3 to 3. So I get 4/3 the tan inverse of, putting in 3, I get 1 minus the tan inverse of radical 3 over 3. And again, I'm going to leave that to you and your unit circle skills to complete that. Okay, this is an interesting problem. Anytime the exponent on the top is bigger than the exponent on the bottom, remember we have to do long division before we can simplify that. So I have x to the 4th, and since I'm dividing that by x squared plus 1, I'm going to have to make sure all of my powers are represented. So that'll give me plus 0 x cubed plus 0 x squared You know what? Let's do that easier. There's an easier way of doing that. Work smart, not hard. Can I write this as x squared plus 1, x squared minus 1, all over x squared plus 1? Okay? So x squared, this is going to go over this 1 with the remainder of x squared minus 1. So this will be 1 over, how would I do that? Maybe I am going to have to use long division. So I know that canceled, but then I'm left with x squared. Oh, that's what it is. Then I'm going to have x squared minus 1 over, yeah, let's do long division on that. I don't remember doing this problem in class. But let's just use long division. X squared plus 1, and then I have x to the 4th plus 0x cubed plus 0x squared plus 0x plus 1. So x going to x squared times. That gives me x to the 4th plus x squared. And subtracting that, I get negative x squared. So x squared goes into negative x squared 1 time. And then that's going to give me negative x squared minus 1. Add, so I get x squared minus 1 plus 2 over x squared plus 1. Okay, there we go. All right, so integrating this, now I have to integrate all of this. Don't worry, it's not that bad. Integrating this, I get 1/3 x cubed minus x plus, this is tan inverse. So this would be 2, the tan inverse of x. That's pretty much it. I told you once you did that, it wasn't bad at all. Just had to do the long division. Okay, so this one, we need to figure out what we can do for this. If we can't do a u substitution, but I can make, because if I did a u substitution, if I let u equal t to the 4th plus 16, I get if u is equal to t to the 4th plus 16, then du is equal to 4t cubed, and I don't have a t cubed, so I can't use the u substitution, but I can make u equal to t squared. So then du is equal to 2t dt. So I have t dt in my problem, so I can make this 1/2 du is equal to t dt. So how do I rewrite this? So I have 1/2 du, and I have u squared plus 16. Well, a is 4, of course. So this gives me 1/2 the tan inverse, because I also need to deal with the a, so that gives me 1/2 times 1/4 the tan inverse of u over a plus c. And of course we can clean that up. 1/8 the tan inverse of t squared over 4 plus c. Okay, so I think these are the last two problems. And I know there's a problem like this on your test, so you want to make sure that you can do it. So if I'm looking at this problem, I can't do a u sub. But if I complete the square, I can make it a tan inverse problem. So to complete the square, I get x squared plus 4x plus some number plus 13. But to keep this equation balanced, I have to subtract what I add. To determine what I add, I take half of this and square it. So half of 4 is 2, and 2 squared is 4. If I add 4, I have to subtract 4. So this becomes x squared And factoring this, this becomes x plus 2 squared. If I were to factor that, I get x plus 2 times x plus 2. And 13 minus 4 is 9. So technically, this is tan inverse because my u is x plus 2 and my a is 3. So I write this as the tan inverse, well, first of all, I have to do the 1/3 on the outside, of u, x plus 2, over a. Okay? Same thing for this one. I think on your paper it's plus, so I changed that one to a plus just to be consistent. But let's go ahead and complete the square. X squared plus 6x plus some number plus 15 minus that same number. Okay, so what number do I add there? I take half of 6, which is 3, and square it and get 9. So if I add 9, I have to subtract 9. And factoring this gives me x plus 3 squared. And 15 minus 9 is 6. Yeah, 6. 15 and 9 is 6. Okay. So then my a is the square root of 6, which is okay. So then I have 1 over the square root of 6, the tangent inverse of x plus 3 over radical 6. And no, I don't have to rationalize that. And that's my answer. Okay, that's it for transcendental functions. The next video will be on L'Hopital's rule, and I'll see you for the next video.